welcome to this session of Mathematics for Social Sciences 1. I am your course lecturer, Mr. Malama Shadrick, and I will be taking you through this course. I wish you success even as we begin this module. So for the first session, we'll be dealing with set theory and its applications in business and social sciences. Of course, taking for granted that we have two sets of students in taking this course. We have those doing business and those doing social sciences in form of economics and finance. All right, so like I said, we'll begin with set theory, and the first thing that we'll need to do is define what a set is. Okay, define what a set is. So a set, okay, a set is a definite and well-defined collection of objects. Okay, well-defined collection of objects, underline definite and well defined. Okay, so these objects we term as elements. Okay, now why is it important that we underline these two phrases? Okay, I'll explain a little bit. Okay, a set will qualify to be a set if it is definite and well defined. What do we mean? If I give an example to say I have a set of students at ICU, this is a definite and well defined set because number one, we have ruled out all the possibilities of including students outside ICU. Okay, we are only including those students that are within the confines of ICU. So students of Mulungushi, students of UNZA, students of Lusaka University are disqualified from this set. So we're only concerned with those students at ICU. All right, those students at ICU. Okay, the other example I could give is a set of vowels. Okay, a set of vowels. Okay, a set of vowels. Let's set A be a set of vowels. We know this will be R, A, E, O, and U. Okay, A, E, I, O, and U. All right, this is a set of vowels. Okay, it is definite and well defined. Okay, so we are only including those letters in the English alphabet that are found that are defined as vowels in this particular set. Of course, that means consonants are disqualified from this particular set. Okay, now how do we represent sets? Okay, set representation. Okay, we represent sets in two ways. The first way is through what we call tabular method. And the second way in what we call set builder notations, or what we call the rule form. Okay, let's look at these individually. What is the tabular form or tabular method? So now in this tabular method, elements of a set are listed and separated by using commas and enclosed within brackets. Okay, so for example, I would say a set of natural numbers less than 7, for example, a set of natural numbers less than 7. So a set of natural numbers less than 7, this set will include 1, 2, 3, 4, 5, and 6. Okay, this is a set of natural numbers less than 7. Okay, now let's move on to the second method of set representation, which will be through set builder notation or rule form. Now, what is this set builder notation or rule form? Okay, so for this set builder notation or rule form, we are saying this is where we get a set, okay, and represent it in a way that you will have what we call an arbitrary element. What is this arbitrary element? It's just this element that will represent every other elements in a given set. Or let me say a letter, not an element. A letter that will represent all the other elements within a set. Okay, so how do we go about this? Let's take the same example. This is set A, set A, the set of natural numbers less than 7. Okay, set of natural numbers less than 7. Okay, so let's represent this one in set builder notation. So we are saying, we say x and we say slash, or sometimes others will use full colon, which is read as such that this x, okay, x is natural number less than what? 7. This is how we will represent it in set representation. So this x is the arbitrary element. It's not the natural numbers, you can see, but it will represent numbers 1, 2, 3, 4, 5, and 6. Okay, this one also in other ways you can write it as a is equal to x, such that this x is, of course, the symbol for natural numbers will look something like this, less than what? 7. Okay, this is the other way you would represent such. Okay, so this is how you use the set builder notations. This is how you're going to use the set builder notations. So these are the two ways we're going to represent sets. Okay, all right, now let's move on to the cardinal number. What is this cardinal number? Okay, cardinal number. Okay, what is this cardinal number? This one will refer to the number of elements in a set. Okay, the number of elements in a set. Okay, this represents, okay, so by definition we're saying this represents the number of elements within a set. Okay, the number of elements within a set. Okay, so this is usually represented okay by n with the number of elements. Okay, all right, short form for number of elements. Okay, this is how we'll represent a cardinal number. Okay, so for example, let's set A be equal to, say, 1, 2, 3, 4, 5. Okay, the cardinal number represented as NA will be equal to what? 6. No, will be equal to 5. These are 5. 1, 2, 3, 4, 5. Okay, this will be equal to 5. This is how we represent a cardinal number. Okay, this is how we represent a cardinal number. If we say we have let me give another example where we have set B being equal to 3, say, okay, A, E, I, O, and U. Okay, let's add X and X. The cardinal number here, okay, the cardinal number of this set, okay, and B is equal to 6. Okay, we write the n here properly. That's n brackets b is equal to 6. So that's how we are going to write the cardinal number. Okay, that's how you're going to write the cardinal number. Now, element of a set. Element of a set. What is this? What do we mean? Okay, so we're looking at the individual components of a given set. Say, for example, we get set A being equal to A, B, C. Okay, what does this mean? What we are saying is this. If we get, for example, this element B, we can say B is a member of A. Okay, we are saying this B is found in the set A. All right. Yeah, this represents membership of a set. This is a member of this. Okay, so in other ways, or in another example I could give in the same vein, we're saying C also is a member of set A. Okay, this is small letter C because we have small letters in that set. Okay, C is a member of this set A. In the same vein, we can express those that are not in this set. Say, for example, D. D is not a member of A. Okay, D is not a member of A because it's not found in this set A. This is how we can represent this. Okay, now let's move on. And before we even go any further, we need to understand the types of sets. Okay, the types of sets and some of their symbols. Okay, so number one, we have the empty set. Just like it sounds, a set is empty because it has got no element in it. All right, it's got no element in it. Okay, a set with no element. Let me write that one in full. So we are saying an empty set is simply a set with no elements. A set with no elements. Okay, and symbolically you use phi or just empty brackets like that. That's how we're going to represent an empty set. Okay, yeah, right. So then we have what we call a singleton set. This is a set with only one element. Okay, this is number two, not number one. Okay, a singleton set is simply a set with only one element. For example, if we have set A being equal to X, okay, then this means this is a singleton. Okay, this is a singleton. All right, now also we need to understand the kind of sets or the other type of sets, which there are two, of course, which all of these will fall into. All right, there's either a finite set or an infinite set. Sorry, and okay, there are two things: finite set and infinite set. Okay, infinite set. For a finite set, let's begin with a finite set. Okay, so a set is said to be finite if, okay, if the number of elements in that set is finite. Okay, finite, however you pronounce it, but we're saying it's a finite set if the number of elements in that particular set is finite. Okay, what do we mean? That you can easily list down the members of a particular set. Okay, then we can say this is a finite set. Okay, for example, if we have a being equal to A, B, C, D, and E, okay, we're saying A is a finite set. Finite set because, okay, because we are able to list down the elements that are here. We can assign a number to it. Okay, the cardinality of this set is known. All right, so n is equal to 5, n of A is equal to 5, and as such, we can safely say this is a finite set. Okay, what about an infinite set? Okay, what about an infinite set? So for an infinite set, as just the name suggests, an infinite set is that set in which we have the number of elements being infinite. Okay, the cardinality of a set in that set is infinite. All right, so let me just write that down. A set is infinite if the number of elements in that set is not finite. Okay, is not finite. Okay, is not finite. All right, that is an infinite set. Okay, so say we say the number of cats, say in Zambia. All right, that's an infinite set because in as much as we can attach an approximation to the number of cats in Zambia, we cannot really have the exact number. Okay, we cannot really have an exact number. That's an infinite set. Or another example I could give is a set of integers. We know integers run from negative infinity to positive infinity, right? So you have 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7 up to infinity, or 0, -1, -2, -3, and so on up to infinity. So the set of integers is an example of an example of an infinite set. Okay, so because you move from negative infinity to 0 to positive infinity, yeah, or the other way around. So that's the difference between the two. For a finite set, we are able to list down the elements within that set. We're able to count them. For an infinite set is when we have a situation where we are unable to count the number of elements contained within that given set. So these are some of the sets. Of course, maybe before we even go further, maybe we even describe what we call the equal sets. Okay, what we call equal sets. Now, two sets A and B are equal if the number of elements in A is the same number of elements in B. That's number one. Is the same number of elements in B also, okay, also the same elements, and I was going to summarize that, but so that you get the point. Also, the same elements in B are found in A. Okay, are found in A. All right. So this is what we call equal sets. When we have, if we have two sets in this example, A and B, the same elements that are found in A are the same elements found in B. Okay, in character, also in numbers. Okay, in the cardinality. All right. So, for example, A is equal to A, B, C, and the set B is equal to C, B, A. Then these two, we can say A is equal to B. A is equal to B. So in short, what we are saying here is that these sets are equal to two or more sets, of course, but I'll just use two to describe the two sets. A and B are equal if and only if they are improper, what we call improper subsets of each other. Now, what do we mean? This brings me to other types of sets. Of course, we'll discuss them properly. What is an improper subset? Okay, so usually represented by this symbol. If we say A is a subset, improper subset of B, and B is an improper subset of A, these statements are the same, but what we essentially mean is that the elements that are found in A are the same exact elements in B, okay? Or in the other sense, we are saying the elements found in B are the same exact elements in A. All right. So this is what we call subsets. So if improper subsets. So improper subsets have the same exact elements, same number of elements, same in cardinality as well as in character. Okay, so now what does that mean? What that means is that two sets are equal if and only if they are imperfect subsets of each other. All right, that is what we mean by equal sets. Okay, that's what we mean by equal sets. In the same vein, I think it would be important for me to mention a proper subset. Okay, proper subset. Since I've mentioned an improper subset, what then is a proper subset? Now, say given a set A, okay, given a set A, okay, a proper subset of A is a subset that does not have the same number of elements as A. Okay, a subset, okay, a subset of A that is not the same as A. Okay, it does not have the same number of elements in A. For example, if we have a set A being equal to A, B, C, D, E, and a set B being equal to C, D, E. Okay, B is a proper subset of A. Why? Because the number of elements in A, the cardinality in A, is greater than the cardinality in what? B. Okay, then we have a proper subset. Okay, unlike in the improper subset case where we have a situation where we have A is equal to B, both in numbers as well as in character. Okay, so that's the difference. That's the difference. Okay, it's important also. Maybe I mention equivalent sets. Okay. Okay, so equivalent sets are similar to equal sets. So for the equivalent sets, they will have the same cardinality. Okay, they will have the same cardinality but different elements contained within those given sets. So for example, if we have A being equal to A, B, C, and set D being equal to say D, E, F. Okay, these two sets are not equal sets, but they are equivalent sets. Okay, they are equivalent sets because they have the same number of elements. Then I mean they have the same number of elements. Okay, because they have the same number of elements. So A and D are equivalent sets. So we can say A is equivalent to B. This set A is equivalent to B. Okay, so of course there is the other type of set that we call power sets. Okay, so those other we call the power sets. A power set is simply a set of all subsets of a given set. Okay, set of all subsets of a given set. For example, let's get x, which is equal to 2 and 3. Okay, let's get this set. What are the subsets of x? Okay, the first subset of this x, okay, this first subset, let me list it down. This first subset is the empty set, of course. The empty set is a subset of any set. All right, then we can say, and then we have 2, and then we have 3. Okay, and then we have the set itself, because every set is a subset of itself. Okay, every set, as well as, yeah, those are the subsets of this given set. So the power set of this given set, represented as P x. Okay, x for this is simply the set of all subsets of a given set. So we have empty set, okay, 2, okay, and then we have 3, okay, then we have 2 and 3. Okay, so this is a power set of x. This is the power set of x because it contains all subsets of x. All right, so by definition, we're saying the set of all subsets of a set. By definition, that's what we call a power set. That's what we call a power set. So maybe before we move on, I talk about two more sets. Okay, two types of sets. Lastly, okay, number one, the disjointed sets and the universal set. Secondly, disjoint sets. Okay, and the universal set. I'll start with the disjoint sets. Okay, now two sets A and B. Okay, two sets A and B are said to be disjoint if they have no common elements between them. Okay, if they have no common elements between them, then we have we say A and B are disjointed sets. Okay, so two sets A and B are called disjoint sets. Okay, disjoint sets if there exists no common elements between the two sets. Okay, this is what we call disjointed sets. For example, let A be equal to A, B, C, okay, and be equal to um, be equal to 1, 2, 3, 4. Okay, so A and B are disjointed sets. Why? Because as you can see, the first set has got A, B, C. The second set has got 1, 2, 3, 4. The two have no common elements existing between them. All right. The other example I could give is a set of vowels. And a set of consonants. Okay, in the English alphabet, consonants. I don't know if this is the correct spelling, but we'll pick it as such. Okay, so when the set of vowels and a set of consonants are disjointed sets, right? Because we know vowels are A, I, E, O, and U. All right, the 5 letters A, I, E, O, and U, and the rest of the English alphabet is a group of or a cluster of consonants. So the two have no common elements between them, so we call vowels and consonants as disjointed sets because there's no common element existing between them. Okay, there's no common element existing between them. All right, so lastly, now let me talk about the universal set. Like I mentioned, the universal set. Okay, now a universal set is said to be a universal set if it contains all elements of its proper subsets. Let me just write down that definition here. Okay, a set is said to be a universal set if it contains all elements in its proper subsets. Okay, in its proper subsets. Okay, so an example I could give for a universal set is a set of students at ICU, right? A set of students at ICU. So a set of students at ICU will consist of all those other students doing different courses, right? So some will be doing economics, some will be doing education, some will be doing plumbing if there's plumbing, ICT, and so on and so forth. So it's a universal set because it is an umbrella of all those students doing different courses. We can think of it in terms of schools, of course. Okay, there's the School of Humanities, there's the School of Business, there's the School of Engineering, and so on and so forth. That's an example of a universal set I could give. Okay, that's an example of a universal set I could give. The other example I could give is a set of letters in the English alphabet. Okay, so we'll move from A to Z. So a set of letters in the English alphabet will make up a universal set. Okay, a set of letters in the English alphabet. Okay, is a set of letters in the English alphabet is a universal set. Okay, then also the other example I would give, like I gave, a set of students, at ICU. Okay, that's another example I would give as a universal set. Okay, so see you in the next segment for operations on this set.